Sorry, my controls moved. So yeah, so you got me again. Um twice the fun, I guess. Um so Chital presented uh a lot of principles that tie into my presentation. I'll let you know ahead of time. Um this isn't going to be a step-by-step, here's what to do, but I'm going to talk about general components of a drip irrigation system and why we have that. And Chital covered a lot of that already. So hopefully this kind of reinforces some of that. For those who maybe weren't here when I was presenting previously, I'm the USU Extension Irrigation Specialist. My background is irrigation engineering, and I gave kind of a similar talk the other week, and I said, this is trying to give in a half hour what I spend about half a semester on with my students. So that's kind of what you're getting. I'm not talking here landscape drip irrigation. I'm talking really the principles I'm going to share will cover anything like small plot farming, garden, vegetable garden type. Even these principles would be in large scale farming, or orchards or things like that. And we're starting to see drip systems go in at that scale, not just in our vegetable crops, but we're starting to see it in some of our forage crops, with subsurface drip irrigation starting to be more favorable, for some of our hay fields and pastures. So there's certainly a lot of interest in that. And that's kind of an area we're going to be doing a decent amount of research in, to look at what actually is the water, conservation potential when we switch some of these things like pasture or hay fields into drip systems. Basic components of a drip irrigation system: you're going to have some kind of source. With a lot of our urban settings, that source water is going to be municipal water. So it's already going to have a pretty high water quality when we think about it from an irrigation standpoint. That's not always the case, though. We still have plenty of people pulling off of ditches, some that may have your own well. There's really quite a wide variety of water sources. As we get into our larger farms, it's certainly all ditches, river diversions, or wells. So there's always going to be some kind of source. There's also going to be what I'm going to call the head of the system. And that's where all the filtration is going to be, where any chemical injection would be, and maybe some of the controls. You may have pumps there. There's kind of a lot that could go in a head. From the head, we'll have one or more irrigation zones or blocks. If we were talking like an orchard, we might be calling these blocks. In smaller systems, we often just call them zones. We're talking about a system, anything that is controlled with one valve. So in this example here, we've got two blocks. We turn one on, we turn the other one off with valves that in this case are located near each other, often would be automated. It's very easy to add automation to this type of system. And then you'll have your drip laterals. And a lot of times we spend a lot of time thinking about the drip laterals and less time thinking about everything else. So the drip laterals, this will be your drip tape or your drip lines or whatever. At the end, we have a flushing manifold, and Chital talked about having some kind of flushing valve. Often when we have drip irrigation on the surface, on the ground surface, we have a small valve at the end of the line, and some require you to go manually open them and flush water out. Some are automated so that they kind of self-flush when the system first starts up or something. The idea is that even with filtration, we're going to have a certain amount of sediment in our drip lines. And we're going to have that just from the water, even with pretty clean water sources. We can get chemical precipitation. Chital talked about that, especially in drip systems. In a small garden, we may not be running fertilizer or chemicals through it, but in any very large drip irrigation system, we're usually injecting some kind of acid, at least occasionally, to maintain the system itself. And then often we're running liquid fertilizer through these lines, especially if we're growing in plastic covered beds. That may be the only effective way of applying fertilizers. And so we need to understand that some fertilizers, when they're mixed together, will generate precipitates. And we don't want that. That's a major problem. It makes the fertilizer not very available and clogs drip lines. Depending on water quality, we may have biological growth, usually kind of a bacterial growth within the drip lines. And so often we're injecting acid or sometimes chlorine in systems just to maintain the system from getting fouled. Flushing manifolds are they're just an important thing with a drip irrigation system. They're often overlooked, but they can mean a lot as far as longevity for the system. Another tip to prevent clogging of drip emitters is to have the emitters facing upward when you put a drip line out. If they're facing downward and you have sediment in your line, the sediment's also going to travel along the bottom of the line. So if we put the drip emitters facing upward, then that eliminates or reduces some of that risk. So drip emitters, there's a lot of types. We generally have, I'm going to say, roughly 3 general types of drip products. We can have what you see on the right, which is like a button emitter. You get a tube, you poke a hole in it, and you ram a little emitter into it. Wherever you have a plant or something, you kind of have a lot of flexibility in how that goes in. When you have, then you have what's on the left, which are the top I would call a drip line. I would also call the drip line the one where we attach emitters to it, but we have drip lines that have emitters formed into them, like that purple cutaway shows. You can see an emitter formed into the drip line itself. Often we call it a drip line if it's a thicker walled material meant for to last longer. Maybe you're going to pull it out and reinstall it every year, or maybe it's just going to stay out. With a lot of our vegetable production, instead of using something like that, we use something like the bottom left, where we have what I would call a drip tape. Thinner walled material, usually comes flat on the roll, and so hence the tape, but would have emitters formed within it. Emitters always have some kind of design to try to make water flow relatively uniformly through the emitter. In the case of this clear drip tape example, you can see a brown emitter And I hope you can see that it has kind of a long little zigzag channel in it. Water enters that emitter from inside the pipe and then travels through that little twisty path. That's called a tortuous path emitter, and forcing the flow to go through all those turns takes energy and causes the flow to be a little more consistent from emitter to emitter. And we'll see in a little bit why that's important. Again, here, another example of a drip tape. It's not typically going to be clear like that kind of demo example was. It'll usually look something more like this black one on the right here. And sometimes you'll actually be able to clearly see kind of a little port or orifice where the water weeps out. Sometimes it'll just look like a little cut in the drip line, in the drip tape. In drip line, you'll always see some kind of little hole because you've got a thicker wall that you're dealing with. Okay, so if we go back, I probably should have kept multiple copies of this throughout the slide, but if we go back here, we've talked about the drip laterals and drip lines because that's kind of the most important part. We're going to talk about that head area because I feel like that's another part that really worth kind of understanding what's going on. So in this case, we have a pump. Maybe this pump is a well, or maybe this is a pump off a ditch. We're going to have some kind of water source protection. Chital talked about backflow preventers that you would use if your source is a municipal water source. If your source is a canal, or if your source is a well, you may, and this is something, you know, to check with Department of Environmental Quality or Department of Ag on, you may have different regulations. And so you may be able to use a different type of protection device. But most of the time in drip irrigation, we're going to be injecting something. And so having some kind of protection device is important. And so if we're injecting something, we're going to have a chemical injection tank. We'll have an injector pump. Having a pump that is properly calibrated is important. And having a pump that has an interlock so that if you turn the system off, the pump doesn't keep pumping. That's important. Sometimes that's a pressure switch. Sometimes if you have a well on a pump, you'll have the electricity from the well and the injection pump tied together. So if that pump switch gets shut off, it kills the injection pump power too. And then we have the injector. The injector nozzle itself, I'll show you, I think on this next slide, is an important component. It's not just a matter of dumping water into the line. And then we'll have kind of final filtration. If we have, if we're pumping out of a surface water source, like a canal, we may need some kind of pre-filtration before all of this, a screen or something. Okay, chemication. This on the left is a chemication valve that's designed for agriculture. Some of these might be too large for a lot of the systems that we're talking about in this conference. But the principle is that you have a check valve. You have a valve that will only let water flow one direction, and that is upstream of your injection point. And that and the upstream of that check, there is a drain and an air release. Now, the difference between this and the types of systems that Chital was showing is that those would have yet another check valve upstream again of this drain and vacuum release. The idea is we want to take all pressure off the backside of this check valve, be able to drain that clean, and have the water stuck on the other side of the valve, prevent any chemical from making it back to the water source. This type of check valve is kind of a compromise It's not, you cannot use this if your source is municipal potable water or a well that you would share with your own residential drinking. This is really meant for use on, say, a canal or a well that's dedicated for irrigation use. The chemical injection valve itself, I have kind of a drawing of down in the bottom right, and I wish I had actually put in a picture of a real one. This is a little valve, and in small systems you'd have a little bit different, but if you have a larger pipe, this is a little valve that screws into the sidewall of the pipe and injects the chemical right in the middle of the water stream. This valve also has a little check ball in it, a spring, and almost like a little ball bearing type ball that prevents water from flowing backwards through the valve. So when your chemical injection pump is pumping in, chemical can get into the water, but water can't flow backwards. And the reason you don't want that is you don't want your water to be able to flow back and then into your chemical tank, overflow the tank, and cause a chemical spill. So this is another safety device. Now, filtration. Filtration is tricky. You really need to look at the manufacturer's information for the drip equipment that you're using and see what they require for filtration. They will often give you a specification in terms of mesh size. And that's just what we use. Think of a screen, a mesh screen. That's where this comes from. In larger numbers, it's like wire gauge or metal gauge. Larger numbers are smaller openings. Small numbers, larger openings. The area of white in this table is really the range that we're looking at with drip systems. The coarsest of them are probably going to be in that 120 mesh size. You're talking about a 1/4 millimeter. That's pretty small, pretty large, I mean, in terms of drip. You're usually going to be much smaller than that. You need to look at the manufacturer. If the manufacturer does not provide that information, that might be kind of a red flag. You might say, well, I'm not sure I want this product. They don't even provide adequate technical information. When we look at this thing on the left, what you're seeing is just kind of, I drew a little sprinkler nozzle. The same principle applies to drip emitters. If you have an opening, we have to filter much smaller than what that opening actually is, because we can get what we call bridging. We can get 2 or more particles coming together to clog the nozzle. So if we think about a sprinkler nozzle, maybe we have a sprinkler nozzle that is somewhere in the 1 to 3/16 inch range. Smaller sprinklers, that's the size of the opening. If I only filter down to the size of that nozzle, any 2 particles or more could come together and still clog that nozzle up. The smaller your nozzle is, or the smaller that opening is, the more opportunity you have for bridging with multiple particles. So much so that for drip, we filter to about 1/10 of the opening size. And again, that's tricky to come up with in drip. So we rely on the manufacturers to say what minimum filtration is. If you have a dirty water source, you're going to need multiple steps of filtration. Take off the coarse stuff, maybe even with a pre-screen before even the pump and everything, and then finer filtration later. For small systems, we really only have 2 real common types of filters. We have screen filters and disc filters. Screens are literally just a screen. Water comes in here on the left, blows out through the middle of a screen. So think of it as kind of trying to inflate that screen. It doesn't want to collapse it if the screen gets clogged. It wants to keep it round. Flows into the outside annular space and out. These can get small enough for drip systems, but not small enough for some drip systems. Disc filters, going to probably cost you a little more money, but have a lot more flexibility. And in this case, water starts on the outside, flows in to the discs and out. So it's actually kind of exact backwards flow scenario. Here is a picture of a disc filter. This is a small one, like a 3/4 inch job. And that's kind of what the body looks like on the left. If we take the bottom out, you can see the stack of discs. Those get compressed when the bottom is put on and the spring engages. You take it out and the discs come apart, and you can wash out the collected material. Automated disc filters will actually run clean water back through the discs, force them open, force the filtrate out, and then blow it out a small valve at the bottom of the filter. Okay, so that's kind of where I'm going to leave it for drip components. Really just some things to consider. Now I want to talk about when we do design, and I'm not going to spend a ton of time on this, but we need to remember that the goal is to give every plant equal access to water, assuming they all have the same water need. You can go back to Dan's presentation earlier about, hey, make sure that the plants have a similar water need that you're irrigating in one zone or block. If your production is small and you don't have all the same plant type in a certain block, let's make sure they're similar, plants with similar root zones and water requirements. This is what we want, a uniform application. Here's what we really get. With any irrigation application, we're going to get a range, some over irrigation, some under irrigation. We can't help that. We want to minimize those differences because those differences are money. They're extra water pumped or paid for or whatever. They can be suppress crop production. It can be even nutrient leaching. So one thing to consider, causes of non-uniformity. What can cause water to be applied non-uniformly? One is the emitters themselves. The emitters are not all perfectly identical. There's manufacturer variation. Good emitters should have what they call a coefficient of variation, a CV, which is, if you harken back to the painful days of your statistics, that is a standard deviation divided by the average. A CV of 3% is kind of our benchmark number here. A lot of times they'll say coefficient of variation or CV less than 3%. And that's a lot of the higher end manufacturers will that's just what they'll say. If they give a number larger than that, just use caution. Just know that you will have more non-uniformity, or you'll have less uniformity. How about that? Just because of that alone. And so you can see it here. If this was a 1 gallon per hour emitter, the one with the smaller CV has much more emitters in a tight area around 1 gallon than the flatter red line does. Okay, another cause is just pressure variation. Chital talked good about the variation of pressure just caused by friction loss in a system. Here's an example, 100 feet of 1/2-inch drip tubing. We have, probably 1.5. Oh, wait, let's see here. Sorry. The red line is pressure. We have maybe a 2 to 3 PSI difference in pressure just because of friction through the line. And the blue line is what that does to to our discharge. You add this variation to the variation from the manufacturer. And here's another thing. A lot of times in our smaller plots, we use really little tubing, like 1/4 inch tubing. You might get that at your garden center or something. This is I'm only showing 50 feet of this because if we go 100 feet of tubing, it's just too much loss. But you can see way more loss, way more variation in pressure and in flow from the smaller tubing than the large tubing. I'm not saying that means you always need large tubing. What I'm saying is you need to be aware that if you've got very large runs, that little tiny tubing isn't going to work for you. Here's what pressure compensating emitters can do for you. Here now I've got a long run, 600 feet, probably longer than we would typically see in a small farm condition. But by using pressure compensating emitters, which Chital also talked about, over a large range of pressures, we can get a relatively uniform application. We look at the blue lines at top compared to the pressure variation in red. That's where the pressure compensating emitters come in. In addition to having maybe a little tortuous path like I showed, they might have a membrane, like a little silicone membrane or something that sits against the valve and compresses with pressure or releases when there's less pressure, that causes the emitter to have more uniform characteristics over a large pressure range. Now, this one's also been talked about. Chital mentioned elevation is pressure. If I have 2.3 feet of water, at the top of it, I have atmospheric pressure. So if I have a pressure gauge, it says 0. At the bottom, I've got a pound of pressure, 1 PSI. It doesn't matter how big of a surface area this is. If this was a little pipe sticking up on end or a swimming pool, 2.3 feet underwater is 1 PSI. When you dive to the bottom of a 10-foot swimming pool, that means that you've got somewhere in the neighborhood of 8 PSI of water pushing on your eardrums, and that's why it doesn't feel good. But it also means that you're going to have, if you've got sloping terrain, that can affect your uniformity. Here's an example of what we might do in a larger system on a slope. We might supply drip lines from point 0 here and run some uphill and run some downhill. The downhill is going to gain pressure. The uphill is only going to lose pressure. And so we balance it out so that we get kind of, on average, good uniformity. That's tricky. I wish I could give you a rule of thumb for where that point is. It really depends on the slope and the flows and the size of the pipe. Chital already gave you something about pipe sizing, so I'm not going to go over that again. I wanted to point out something about flow measurement. This is an important part of our systems, and I wanted to point out a resource on my website, which will come up in just a second. The Idaho Department of Water Resources has a published list of meters that they have deemed to be accurate. And you can read the little document about under what circumstances they're accurate under. I highly recommend looking at this. The state of Utah doesn't have anything like this. All of these have been tested at the Utah Water Research Lab up here at Utah State. The water lab is a world-class hydraulic research facility. When I say world-class, I mean world-class. It's there are very few labs that have the capabilities that they have there. And so that's why I feel comfortable putting this up on the website. I'll skip the stuff about air venting and things. We do have a fact sheet that just got published, water recommendations for vegetables, that I encourage you to look at. You can just search that, USU Extension, that talks about how long it takes to run a drip system at certain flow rates, like drip emitter flow rates and drip emitter spacings, to get a certain amount of water applied. That can be also helpful in the design end of things.